Today we will discuss about understanding the Onsager relations using basically we will use two aspects, that means the kinetic and the thermodynamic treatments. This question is sometimes asked in this way: how you can verify Onsager relations, or simply you can say verification of the Onsager relations. What we do basically, we will apply the Onsager theory basically to simple reversible. We will consider a simple reversible reaction and investigate it. First we will investigate it with kinetically and then thermodynamically. Suppose the reaction is given by, suppose A is in equilibrium and K1 is the forward rate constant and K minus 1 is the backward rate constant for this reversible reaction. Okay, so first we will apply this kinetic treatment here. So we will first calculate the rate for A, so we can write minus D. Suppose Ca is concentration of A upon dt, it will be equal to, applying this to equation 1, so we can simply write K1 into concentration of A minus K minus 1 into concentration of B. This is simple equation. And similarly for the B, concentration of B, we will write it as rate will be simply equal to this much, that means K1 Ca minus K minus 1 Cb. This is equation 3. Now we will consider an equilibrium condition. At equilibrium, the macroscopic reaction rate basically we will represent this reaction rate by simply, suppose JCH, chemical reaction rate JCH, which is basically equal to second and third, you can say minus dCA upon dt. It can be also equal to this much. So we know it simply from the kinetics, so we are applying that here. So at equilibrium this will be simply equal to 0. So from this we can simply say that if we compare second and third, we will get this, that means K minus 1 Cb. Suppose this is now at equilibrium, so we will put a superscript E here, representing simply equilibrium state. So it will be K1 Ca equilibrium. And we know K1 is basically the rate of forward reaction and K minus 1 is the rate of backward reaction. So if we rearrange this relation, we can simply write it as K1 upon K minus 1 will be equal to CB equilibrium upon CA concentration at the equilibrium. So we know this is simply equilibrium constant K, because rate of forward reaction upon rate constant for the backward reaction, that will be simply equilibrium constant. So we will represent that by capital K. So this will be equal to now CB equilibrium upon CA equilibrium. Now suppose this is equation now 5. Now suppose at any time t, suppose alpha A is the concentration of A, that can be equal to the initial concentration of A minus the concentration of A at the equilibrium stage. And similarly we can write alpha B is equal to CB minus CB equilibrium. So this is equation 6. Now suppose x moles of A reactive to give, that means we have this equation A equilibrium B. If it is initial concentration was simply, suppose at T is equal to 0, its initial concentration was Ca and its initial concentration was Cb. Now at T is equal to some time, suppose x moles of A have basically reacted to form x moles of B. That means now the concentration will be equal to simply Ca minus x, because from A x moles have reacted to form B, so this will be now Cb plus x. Now its concentration will increase, so we will simply write it as Cb plus x. Here we will write this Ca minus x is equal to, suppose Ca equilibrium and Cb plus x will be simply equal to then Cb equilibrium. So that if we add these two, that means Ca, that means we can write Ca equilibrium plus Cb equilibrium. This will be equal to Ca minus x plus Cb minus plus x. Okay. So here you will see this plus and minus will go, so you will get simply this relation. That means we will write Ca plus Cb, we will write first to this part, it will be equal to now this part, means Ca equilibrium plus Cb equilibrium. So this is now equation 7. So from equations 6 and 7 we have, that means we can simply write alpha A plus alpha b, which is equal to simply equal to, we will put the value of alpha a, that was equal to Ca minus Ca equilibrium, and alpha b was equal to plus Cb minus Cb equilibrium. So we can simply write this as, that means alpha a plus alpha b will be equal to Ca plus Cb minus Ca equilibrium plus Cb equilibrium. From this relation, that means equation 7, we know these two are equal. So this and this whole term minus this, it will be simply equal to 0. So we can simply write then alpha a is basically equal to minus alpha b. Very important result here. So suppose this is now equation 8. Now if the rate of chemical reaction, suppose that was nu, is designated now by as, suppose, JCH. So then equation 2 can be simply written as, that means we can simply write the JCH will be equal to K1 into Ca equilibrium plus alpha A minus K minus 1 into Cb equilibrium plus alpha B. So this is equation 9. Now we have already derived these results, that this K1 Ca equilibrium is basically equal to K minus 1 Cb equilibrium, and this result also, that means equation 8, alpha A is equal to minus alpha B. So we will simply then have JCH will be equal to K1 Ca equilibrium. We are just giving this K1 back to these terms. So we will write these as Ca equilibrium plus K1 alpha A minus K minus 1. Now give this back to this and this, you will get Cb equilibrium minus K minus 1 alpha B. If we look carefully here, we know this much, that means K1 Ca equilibrium is equal to K minus 1 C. That means this term and this term will cancel, and also this alpha A is basically equal to minus alpha B. So here JCH can be written then as K1 alpha A. Here in place of alpha B we will introduce the value minus alpha A, because alpha B will be equal to, here you can simply write alpha B is equal to minus alpha A. So we will introduce this value in place of alpha B. So it will be then plus K minus 1 alpha A. So from this relation we can simplify this relation is equal to, because here it is alpha A, it is alpha A, we can take these outside and we can simply write K1 plus K minus 1. So what we do here, we will simply multiply to this term in the numerator K1 as well as in the denominator K1. So we will get then JCH will be equal to alpha A. If we take now this K1 outside, so it will be K1 here and it will be 1 plus this K1 is gone, so it will be K minus 1 upon K1. So we will write it as JCH is equal to alpha A K1 1 plus, but we know K is equal to K1 upon K minus 1, that means forward upon backward direction, so it will be equilibrium constant. So this comes out to be 1 upon K, that means the capital K here, equilibrium constant here. So this is now equation 10. So this is very important result. So thus we have got the basically the rate of the chemical reaction in terms of these alpha and rate constants and equilibrium constant. So we will keep this as such. Now we will proceed to the thermodynamic treatment. Thermodynamic treatment. Now here we know basically that the affinity, that is basically the generalized force. That means A, here it is affinity, or you can say the generalized force or simply force, you can say, is equal to, we can simply take the definition of this affinity. We know it is the difference of the chemical potentials here, so it will be mu A. Here remember this is reactant A, so I have written this capital A with some marks here, so it is affinity. So don't confuse this affinity with A. Okay, so it is now mu B. This is equation 11. Now we know the flux, that is the rate of chemical reaction according to the Onsager theorem, is proportional to generalized forces. That means we know JCH is basically directly proportional to this A, the generalized force, here affinity, and we can replace this proportionality by proportionality constant, so that will be the phenomenological coefficient. So then A here affinity, so but from equation 11 we will put the value here, so it will be L into mu A minus mu B, that means the chemical potential. So this is equation 12. Now for an ideal system, basically if we take an ideal system, but that should be at constant temperature and pressure, the chemical potential of the species basically is given. Of ith species, if we take we will take a generalized case, that means we can simply write the chemical potential for the ith species. I mu I is equal to mu I standard plus RT ln of Ci. Here mu I naught is basically the standard chemical potential, R is the gas constant, T is the temperature, and C is simply the concentration. Okay. Now what we do, we will basically substitute the values from substituting for C here concentration from equation 6. That means we can write C, first we will take a generalized situation, C equilibrium plus alpha, or we can also write it as what we do here, we will multiply this term by C equilibrium in the numerator as well as in the denominator. So this will be, and take this CE as common, and we will get 1 plus alpha upon CE. So we will take this generalized situation and apply to reactant A and the B as well. So we will get, and chemical potential of A suppose will be equal to then mu A naught plus RT ln. So in place of C we will write it CA, because for A, so we will write it as CA equilibrium here, and then we can put 1 plus alpha CA equilibrium. So this is simply log m into log n, so we can simply give this natural log back, so we can write this as mu A naught plus RT ln of CA equilibrium plus RT ln of 1 plus alpha CA equilibrium. Okay, so this is equation 14. Similarly, we will take chemical potential of B. So we will write chemical potential of B is basically equal to mu B naught plus RT ln of, so in place of Ca we will replace it with the Cb equilibrium. Rest will be the like same situation, so we will separate this into log m into n. So we will write simply RT ln of 1 plus alpha. Suppose here it will be alpha A, it is alpha A here, so it will be alpha B upon Cb equilibrium. Cb equilibrium, so this is equation 15. Thus we can put these values and we will write the affinity will be then equal to, using this mu A and mu B values we can simply write equal to, that means putting into the equation 11 these values 14 and 15, we will write mu A naught plus RT ln of Ca equilibrium plus RT ln of 1 plus alpha A upon Ca equilibrium minus mu B naught plus RT ln of Cb equilibrium and minus RT ln of 1 plus alpha B upon Cb equilibrium. So this will be equation 16. We have just put the values of 14 and 15 into equation 11. Now we know at equilibrium basically the chemical potentials will be same for A and B. That means mu AE is basically equal to mu B. Superscript E just confirm indicating equilibrium condition. So if we look into equation 16 very carefully, it means this part and this part, they will be simply cancelled out. That means they will cancel, so we will get simply the affinity will be equal to RT. Now these two terms will remain here. First we will take RT is multiplied to both the terms, we will take it outside, so we will write it as ln of 1 plus alpha A upon Ca equilibrium minus ln of 1 plus alpha B upon Cb equilibrium. This is equation 17. Now if we take a condition, that means this suppose for if alpha A upon Ca equilibrium is less than 1, and also this alpha b upon cb equilibrium is less than 1, then we can take simply the ln of 1 plus alpha a upon ca equilibrium approximately equal to alpha a upon ca equilibrium, and similarly this ln of 1 plus alpha b upon cb equilibrium will be also approximately equal to alpha b upon cb equilibrium. Therefore the affinity, that means the generalized force, then will be equal to RT, and we will get these terms alpha A upon CA equilibrium minus alpha B upon CB equilibrium. And similarly we can write this equation as RT alpha A upon CA equilibrium. We know this, basically we have derived this alpha A is equal to minus of alpha B. So in place of alpha B we will put minus. Alpha B will be equal to minus alpha A, so it will be simply plus, minus minus will be plus, and you can write simply alpha A upon CB equilibrium. Okay, so this is equation 19 and this is 18. So what we do here, we will now take this alpha A outside the brackets. We will write it as RT alpha A. So inside will be simply 1 upon CA equilibrium plus 1 upon CB equilibrium. Here we will do simple multiplication of CA equilibrium in numerator and CA equilibrium in the denominator to this term. So this affinity will then be equal to RT alpha A. Now we can take this CA and this CA equilibrium outside, so we will write upon CA equilibrium. So inside we will get only 1 plus CA equilibrium, this term will be there, upon CB equilibrium. So this is equation 20 now. That means we can also write, but we also know that this CB equilibrium upon CA equilibrium, we have already taken it equal to the equilibrium constant. So we can write this as this affinity basically affinity will be equal to RT alpha A upon CA equilibrium into 1 plus 1 upon equilibrium constant. So capital K. So this is now equation 20. We will simply substitute this value, substituting for affinity. Here you have to remember this affinity from this equation, that means equation. So okay, here this is 20, so this will be 21. Okay, equation 21 in equation basically 12. So we will simply obtain this TCH will be equal to L into A. We have this equation to L equation. So in place of A we will simply insert the values RT alpha A upon CA equilibrium into 1 plus 1 upon K. This equation is basically this 22 is derived by assuming that reaction is close to the equilibrium. That means we have simply used this alpha I equilibrium for generalized case Ci equilibrium is less than 1. Now this is the kinetic treatment, this thermodynamic treatment here, this one, this relation. Now if we compare the kinetic and the thermodynamic ones, that means comparing equations 10 and 22, that means the kinetic one and the thermodynamic one, we will obtain basically that JCH is basically equal to, first we will write this thermodynamic part here, so it will be L RT alpha A upon CA equilibrium into 1 plus 1 upon K, which will be equal to the kinetic one. We have already derived alpha A K1 into 1 plus 1 upon K. So this is an equality, so this part and this part will cancel, and also this alpha A and alpha A will cancel here, so we will get this much, that means L T upon CA equilibrium is equal to K1. K1, or we can write the phenomenological coefficient out of this equation. L is equal to, L will be equal to simply K1 CA equilibrium upon RT. So this part basically K1CA into equilibrium, we will write it as nu F equilibrium upon RT. So what is nu F here? It is simply the rate of the forward reaction. forward reaction but at equilibrium. Now this equation suppose now we will name it, give it a number, suppose 23. It basically shows that the phenomenological coefficient here, phenomenological coefficient, that means this L, depends on the simply the equilibrium concentration. Equilibrium concentration of A. Here you will see it depends upon the CAE, that means the equilibrium concentration of A, that means simply CAE, but at a given temperature. A given temperature. So this relation basically verifies the Onsager relationship. Okay, thank you.